Okay, so this is the second lecture of Chapter 2, and we're going to talk a little bit about chemical bonding. That's ionic, covalent, hydrogen bonding, and van der Waals forces. We're also going to talk about pH and what pH scale is, and also kind of what the ions that are in charge of pH are and how they work. Okay, so last time in Chapter 2, Lecture 1, we discussed atoms and molecules and compounds and subatomic particles, and so that information is going to be really important as we move into chemical bonding, because we're bonding between atoms and we're using subatomic particles like electrons to do that bonding. Okay, just right up front, we're going to talk about ionic and covalent. Those are probably the most important two types of bonds, but they're probably the most popular bonds when you start talking about bonding also. So ionic bonding is when one or more electrons are transferred from an atom and you're bonding between ions. Okay, and I have a picture, and we're going to get into some more information in a minute, but ionic bonding is when you take one atom, and I know this atom, sodium, has more than one electron, but there's only one electron in its outer orbital, so we're just focusing on that one. And then chlorine has more than 7 electrons, but we're just going to focus on the 7 because those 7 are in the outer electron orbital. Na, or sodium's going to give up one because it's easier for it's easier for sodium just to give up that electron than it is to receive 7, and chlorine is easier to receive 1 than to try to give up 7. Okay, and so sodium will give up a chlorine. Chlorine becomes negative because it received an electron. Sodium becomes positive because it got rid of an electron, and because there is a positive and negative charge, they bond together, kind of like magnets. Okay, covalent bond is a much stronger bond. Ionic bond is much weaker. A covalent bond is an electrons, or that the electrons are shared between atoms. Okay, so ionic bond is a transfer of electrons. Covalent bond is a sharing of electrons, and this picture shows a polar covalent bond. It's actually forming water. Okay, 2 hydrogen atoms are going to be attracted to and share the electrons with an oxygen in 2 different places, causing H2O. Okay, but we'll get into more of the specifics in a minute. Hydrogen bonds are the third type of bond, and really important in life because we're talking usually about water and the bond between water. But you can see the hydrogen bonds are between a hydrogen of one molecule and a negatively charged atom of another molecule. In this case, it's oxygen. Okay, so when this water molecule bonds with this water molecule, it creates a hydrogen bond between the 2 molecules, and that's really important for all the properties of water, and we're going to talk about those today. Okay, covalent bonds are stronger. Ionic bonds are weaker than covalent but stronger than hydrogen. Hydrogen bonds are the weakest type of bond until you get to van der Waals forces, and I don't know that they're really considered a bond, but we call them van der Waals forces. These forces can be seen when lizards, like geckos, climb up really smooth surfaces. Okay, they've got a lot of surface area. You can see their toe pads are striated, and so it creates or increases surface size or surface area, and allows the opposing sides or opposing regions to attract. Okay, there would be opposing negatively charged regions between it and the substrate that it's climbing on. There would be also opposing positive regions on the toe pads and the substrate it's charging on or climbing on. Okay, so let's get into the bonds a little more deeply. Remember that bonds are attractions by sharing or donating electrons between atoms. Remember, electrons that are transferred or donated are ionic bonds, and electrons that are shared between atoms are covalent bonds. But then you can also have bonds that are just between unlike charges, which would be the case in hydrogen and van der Waals forces. Okay, reactions are making or breaking chemical bonds, and when you make or break chemical bonds, you're always going to exchange a certain amount of energy. Okay, when you make a bond, you're going to be storing energy, and when you break a bond, you're going to be releasing energy, which is really, really important when we start getting into the energetics of cell respiration and photosynthesis. Okay, but the bonding is always at the electron level. Right? You can see over here there are several different examples. H2 would be a molecule of hydrogen. O2 would be a molecule of oxygen. You can see that this would be a single bond. It's usually written like this. Double bond means that oxygen bonded twice with itself, and so you get a double bond. CH4 is methane, and so you can see 4 bonds, which is really important because carbon is the central atom, and carbon's really good at being a central atom because it can bond up to 4 times. And when we get into the biochemistry here in a few lectures, really next lecture, you're going to see why carbon's so important and the really awesome properties of carbon that allow for life to exist. Okay, water is H2O. We already talked about it, but you can see it here. It's a double bond, really. Well, it's 2 single bonds between oxygen and hydrogens. Okay, so let's talk about reactions in living things or in living cells. We're talking about covalent bonds. Covalent bonds, remember, are sharing of electrons. It is a very, very strong bond, and it's a bond between 2 or more elements, and those elements have to be sharing electrons. Okay, the goal of any bond really is to always fill the outer energy level, and in these bonds it is no exception. Okay, you can have 2 electrons in the first level, okay, and if you look at all of these atoms, there are always 2 bonds in every first orbital, okay, or 2 electrons in every first orbital. Then you can have 8 electrons in all other orbitals. And I know when you get into chemistry and you start talking about some high-level chemistry, you're going to start talking about some variation among other orbitals. But for now, as long as you know that there's 2 electrons in the first orbital and there are up to 8 in every orbital after that, you'll be good. Okay. Hydrogen, atomic number 1, has 1 proton in the nucleus, 1 electron in the orbital. Okay, and it can bond basically 1 time because it needs to fill its outer energy level. Carbon can bond 4 times because, see, you have an open carbon here, or an open electron, open electron, open electron, open electron, and so you want to fill all 4 of those locations in order for that outer energy level to be full. Nitrogen can bond 3 times because there are 3 open electron spots. Oxygen, it can bond 2 times, okay, which is why it makes H2O. It bonds a hydrogen here and a hydrogen here. All of those cases would be sharing electrons, and so it would be a covalent bond. Ionic bond is very different, okay? You're still using electrons. You're still trying to fill or empty an outer energy level because, remember, bonds or atoms are a lot more stable when they have an energy level that's full, okay? And you can do 1 or more electrons given away at a time. Just like we said in that first picture, sodium is going to give up an electron because sodium is, I don't want to say lazy, but sodium, it's easier for sodium to give up 1 electron than to try to hunt down and receive 7 to fill that outer energy level. It doesn't matter what energy level is full as long as the outer energy level is full. Okay, so it's easier just to give up this 1. And it's easier for chlorine to receive 1 than to try to find a source for all of the 7 that it would need to get rid of in order to fill this second outer energy level. Okay? When sodium gives up 1 electron, it released 1 electron, which is negatively charged, and so now it has 1 extra proton than it has negatives, and so it has a positive charge. And you can see it over here. It created an ion. Okay? This is an ionization process. Chlorine received a negatively charged electron, and so because it received 1 extra electron, which is negative, and now it has 1 extra electron versus the number of protons, it has a negative charge, and so it became a negative ion. The attraction between this positive and negative charge, just like I want to say batteries, but just like magnets, snap together between the opposite charges. That's what's happening here. Okay, is it easy to pull magnets apart? Yes. It's easy to pull these ions apart. Okay, this is not a very strong bond. It's a weak bond, but it creates charged atoms called ions, which are really important when we start getting into, like I said, photosynthesis, cell respiration. And when these snap together like magnets between these 2 charges, it creates NaCl, and NaCl is sodium chloride, which is salt. Okay. Hydrogen bonding. Hydrogen bonds are, like I said, between hydrogen of 1 atom and a negatively charged atom of another molecule. Okay. It does not share electrons, so it's not very strong. Okay, in fact, it's a very weak bond, and it's just like an ionic bond in that opposites attract. Okay, but it's not transferring electrons like ionic bond. It's just there's a partial positive side on this hydrogen, and there's a partial negative side on this water or oxygen, and it's based on where the electrons are kept. Okay. And so when you have a partially positive and a partially negative and they attract together, these two molecules are going to be held closely together, and it's going to create cohesion and adhesion, which are really important properties that allow life to exist. Okay. So if we talk a little bit about the water molecules, you can see this is a water molecule, this is an oxygen, this is two hydrogens, and these little blue dots are the electrons. And so if you think about, there's a negative, 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 negative. Okay, this one right here is positive, positive, and then you have a bunch of positives in the nucleus. But where are all of the negatives, or most of the negatives, kept? They're all up here, right? There are a lot of negative charges on the oxygen side of this water molecule, and so we call that partially negative. And are there any negative charges on the outside of these hydrogen ions? No. Okay, or I shouldn't say ions, but these hydrogen atoms? No, and so we call these over here partially positive, and I make this little fish symbol because that's our partial sign. And so this side of the molecule is partially positive, this side of the molecule is partially negative, and it's just because it's where the electrons are kept. And so these positive atoms are going to bond with the partially negative side of the next oxygen of this water molecule. Okay, remember, if these are the hydrogens and are partially positive, and these are partially positive, this side over here is where all the electrons are kept, and so this is going to be the partially negative side. These right here are the hydrogen bonds. Okay, when water sticks to water, it's called cohesion. Water molecules sticking to other water molecules. Cohesion, just like co-workers are two workers that work at the same place. It's a bond between two like substances, so it would be water sticking to water. Adhesion, just like adhesive tape, is sticking non-like things together. I could just take a poster to the wall or something like that. And so water sticking to other non-water molecules would be adhesion. And you see it all the time. Water sticks to the side of your car after it rains. Water sticks to the side of your house. Water will stick to the sides of a glass container. Okay? When you look at a graduated cylinder and you put water in, you get something that looks like that, and that's called the meniscus. And so what's actually drawing the water up into the sides is this property of adhesion. Okay, water wants to stick to the sides of the container, and so it actually kind of climbs up against gravity, and so that's adhesion. Cohesion would be all the water molecules down in here sticking to all the other water molecules. Okay, and that's creating a liquid, and that's allowing water to stay in one big mess. So let's get into a little bit about solutions and suspensions. This is talking about pH and what mixtures and solutions are. Mixtures are materials that are mixed together but no chemical or physical change is taking place. So when I mix cereal in with water or milk, or I mix multiple different types of cereals together, or I mix chips into my cereal or whatever, I created a mixture. Because I can still separate out the chips and the cereal and the milk. I mean, it might get all kind of, messy and stuff like that, but mixtures are things that are mixed together that have not allowed a chemical or physical change to take place. I can still separate them out. Okay, think about salad. You put all these different vegetables together and create a mixture. It's one kind of thing called salad, but you can still take out and separate the salad lettuce from the carrots, from the cucumbers, from the tomatoes, from the dressing, and stuff like that. Okay, that's a mixture. Solution is when the substances are evenly distributed throughout and no chemical change is taking place, like you mix salt into water, or you mix sugar into water, or you mix Kool-Aid powder, or you mix food coloring into water. Okay, it is really, really hard to separate the food coloring out of the water because there's been kind of this physical change take place. It turned colored water that's really concentrated in the food coloring into less concentrated colored water in the water. Solute is the substance that is being dissolved. Solvent is the solution or the substance that is doing the dissolving. Okay, so when I mix sugar into my water, okay, because I want something really sweet, the solvent is water, okay, or water is the solvent because it's doing the dissolving. Solute would be the sugar because it is being dissolved. Okay. So acids, bases, and pH. Water is polar, and I mean polar because it has that partial positive side and the partial negative side. And so when a molecule has both of those sides, like a water molecule does, it is said to be polar. When a molecule doesn't have a partial positive and a partial negative side, it just has an even charge throughout the whole thing, it's said to be nonpolar. Okay, so water is polar and encourages ions to separate, which means it's a good solvent. And in fact, we call water the universal solvent because it really dissolves everything or most things, except for nonpolar things like water or oil. Some chemicals, though, when they are dissolved, will give up H plus ions, and others will give up OH negative or hydroxide ions. Okay, pH is the measure of these ions in a solution. Okay, and so acids are going to be a high H plus concentration. Bases are going to be a high OH negative concentration. Okay, all solutions are going to have both in them. But if you have a higher H plus concentration than you do OH negative concentration, you're going to be an acid. And if you have a higher OH negative concentration than an H plus concentration, you're going to be a base. Okay, and buffers are weak acids or weak bases that resist change in pH. And we'll have a lab in class in a few days that that outlines what buffers do, and so that you can see that working in action. Okay, a little bit about acids. They are 0 to 7 on the pH scale. Remember, pH is neutral, okay, or 7 is neutral, and so the range is from 0 to 14, with 7 being right there in the middle. Okay, so 7 is neutral. If you are on the lower side of neutral, meaning 1 to 6.9, you're said to be acidic, and if you're 7.1 to 14, you're said to be basic. Okay, pH of 1 is very acidic, and as you go towards 7, you become less acidic and more basic. Okay, pH is calculated as the negative log of the H plus ions. Remember, the more H plus ions you have, the more acidic and the lower your pH. So it is a kind of an inverse scale, right? Which is why it's a negative log. And it's a base 10 scale, meaning every step on the scale means you're 10 times higher or lower on the number of H plus ions. Okay, so if we have a pH of 4, you have 10 times more H plus ions in the solution than a pH of 5. And if you have a pH of 3, you have 100 times more H plus ions than a pH of 5. Okay. Here's our pH scale and some of the kind of random things you might see around your house. Like if you think about battery acid, that is incredibly acidic, and it's down here at like 0.3 pH, okay, on the pH scale, which is very, very acidic. If you think of lemon juice and vinegar, those things are probably at your house all the time. They are pretty acidic as well. Okay, they're like 2.2 to 2.8 on the pH scale. Milk is acidic, but it's getting closer to the 7 range, so it is just like 6.2-ish on the pH scale. Blood is a little basic, and that's important when we start talking about some of those things later in the year. But as you get up towards this alkaline or very basic section, you're going to get into household lye, bleach, and a lot of your ammonia and cleaners. So those are extremely basic. Okay. So what are bases? Bases are the exact opposite of acids. Remember, acids are measured from 0 to 7 on the pH scale, and so bases are measured from 7 to 14 on the pH scale. And bases have a very high OH negative concentration. Remember, if the concentration of OH negative increases, the concentration of H plus has to decrease. And if the OH negative increases, the pH has to increase also, because we're getting more basic, right? So we're going from like 7 to 13. The exact opposite happens if the H plus ions increase, then our OH negative has to decrease, meaning our pH has to decrease, right? So the correlation between H plus and the pH value is inversely related or inversely proportional. The relationship between pH and our OH negative ions are directly proportional because they are the exact same. As one goes up, the other goes up. Buffers are those weak acids or bases that resist change in pH, meaning they keep your solution stable, or they try to keep it stable, which is really important in maintaining homeostasis. We talked about what homeostasis was. That's maintaining a constant internal condition. Okay. And if you can't resist change in pH, like if you're an organism that finds himself in a really acidic pool of water and you can't control the pH in your blood or can't control the pH in your body using buffers, you're going to be in trouble. Okay, and so buffers don't work indefinitely, but they work for short durations that allow the organism to maintain that pH at all times. Okay, you don't want to have wide changes or vast or large changes in your pH all the time, because that requires, that's going to allow enzymes to not function correctly, and it's going to lead to denaturation, just like the temperature we talked about last time. Okay, that's going to do it for today. Study hard, keep up with your notes, keep up with the quizzes. See you in class.